Most enterprise AI rollouts rely on basic conversational prompts, and the result is chaos. When operators throw unstructured instructions at complex models, the outcomes are defined by high variance, factual drift, and stylistic inconsistency. Large language models do not independently decide to produce brilliant or mediocre work. They mirror the input. This is cognitive scaling. The intellectual caliber of the output depends entirely on the structural clarity and semantic density of the text you provide. This relationship is mathematically observable. Plotting prompt sophistication against output complexity yields a nearly perfect linear correlation of 0.925. These models act as cognitive multipliers, granting operators of structured systems far more utility than unstructured requests. Achieving deterministic, production-ready results requires moving past the idea of the magic prompt. Success in an enterprise environment requires engineering deliberate, rigorous cognitive scaffolding. The public release of these models conditioned us to treat them like search engines or basic chatbots, typing a single sentence and expecting a completed task. Single-turn instructions are fragile and prone to failure. A systemic pipeline, however, survives edge cases by dictating exactly how the model should process information. A true prompting system is a repeatable, deterministic framework. It is designed to elicit predictable, high-quality results across varying operational domains, turning a volatile model into a reliable engine. Without explicit mathematical and semantic boundaries to guide the underlying transformer architecture, natural language interfaces drift toward hallucination. Transitioning from theory to deployment requires looking at the empirical evidence behind structural constraints. Structured prompting architectures improve output accuracy by 45% over simple queries. Iteration cycles drop from 3.8 to 2.0, and first-pass acceptance hits 55%. The system achieves 95% adherence to structured schemas like JSON, providing a 76% error reduction rate. These metrics represent the boundary between an immediately deployable asset and wasted compute costs. To translate raw human intent into deterministic instructions, engineers utilize the CRAFT framework. It is a 5-part architecture that maps operational parameters into precise semantic instructions. The C stands for context. Instead of pulling broadly, context establishes strict domain boundaries. It explicitly defines the operational variables: creator, product, target audience, and competitive constraints. R is for role. Assigning a specific expert identity, like a senior product strategist, shifts the latent token generation pathways towards professional terminology, eliminating generic outputs. Action specifies the exact imperative verb, paired with format, which dictates the strict structural layout of the final output, using Markdown, JSON, or XML schemas. Finally, tone and constraints. This sets stylistic frequency, but negative constraints are key, proactively banning repetitive transitions and generic marketing jargon. Defining what a model must not do is just as critical for maintaining structural integrity as its active instructions. Standard models frequently fail on complex tasks when they attempt to generate a final answer directly in a single logical turn. To solve this, developers build multi-stage logical architecture called step-by-step scaffolding or chain of thought processing. By adding a zero-shot logical directive, you force the model to allocate computation steps to intermediate analysis. The model must write out its intermediate deductions inside thinking tags before formulating a conclusion. This forced decomposition identifies logical contradictions and calculation errors early in the generation pathway, long before they reach the final output phase. For stylistic tasks, operators use few-shot semantic patterning. Wrapping optimal examples in XML tags establishes a clear stylistic baseline for the model's pattern matching systems. Advanced scaffolding removes the burden of logical leaps from the model, transforming it into a verifiable reasoning engine. We can see this architecture in practice through an automated educational content production pipeline using Google Notebook LM. This workspace operates in a strict sandbox environment, drawing context only from uploaded source documents to prevent hallucinations. The process utilizes a 5-step automated workflow, moving from bulk competitor URL ingestion to final video rendering. The critical mechanism is step 3, the DNA playbook extraction. Here, structured XML tags bind the model to a specific task, forcing it to analyze competitor transcripts and extract their core structural formulas for tension curves and hook mechanics. To guide the educational narrative, the operator must seed the ingestion context with practitioner frameworks, such as established texts on creative execution and storytelling. The system then cross-references this extraction playbook against local market data to generate high-potential, grounded video concepts. The success of fully autonomous media generation is entirely dependent on the rigor of these underlying XML extraction schemas. We are seeing a significant shift toward high-value product engineering and workflow automation within the enterprise service sector. 86% of enterprise employers are now actively redesigning job roles around AI upskilling. India has become a central geography for this transition. By 2026, AI engineering job postings in India grew by 59.5% year-over-year, the fastest growth rate recorded. This growth is anchored by the expansion of over 1,200 global capability centers that maintain dedicated AI capabilities, moving beyond simple billing. In this environment, engineers with specialized prompting capabilities command premium global hourly rates. On freelance marketplaces, senior specialists command between $80 and $150 per hour, with Gen AI architects commanding domestic salaries of up to 60 lakh per annum. Mastering structured context has become a primary differentiator in the enterprise economy. As these systems scale, enterprise architects must identify the exact point when it makes sense to transition from manual orchestration to fully autonomous agentic loops. Executing a manual prompting system involves a linear, predictable cost as tasks increase. Conversely, autonomous agentic workflows require high upfront capital, but minimal intervention keeps their trajectory flat. The math intersects around month 4. Beyond this break-even point, time savings scale exponentially. For custom, rapidly changing, or low-frequency creative tasks, manual prompt design remains significantly more cost-effective, as the development overhead of agentic systems is difficult to amortize. Whether you are executing a single query or orchestrating a massive network, the ultimate ceiling on your deployment success will always be the rigorous clarity of your cognitive scaffolding.